Hello everybody and welcome to my first official calculus video. Well, the first thing that we had was, you guys all know, before you left, we took a quiz test kind of thing. Obviously I can't give those back to you, so let's skip right over the reflection. Right away, we're going to get right into what are parametric functions. And parametric functions, what we're doing here is we're trying to go from one dimension into two dimensions. So what we have is we have two different functions. X and y are both a function of t. If f and g have derivatives at t, then the parametrized curve also has a derivative at t. And you can see I got a little bit excited about that one. My bad, my bad. All right, so here's the way the book puts it. If x and y are given as functions, x is equal to f of t, y is equal to g of t, over an interval of t values, then the set of points xy is equal to f of t, g of t, defined by these equations, is a parametric curve. The equations are parametric equations of the curve. And I'm not going to spend a whole lot of time leaving this on the screen. If you want to get that, just make good use of the pause function on YouTube and just pause it and get it off of there. That way we can try to get through this pretty quickly. So the first thing that we're going to do is we're going to work on graphing parametric functions. And you guys did this last year. It was part of trig pre-calc. We did this by hand, but what I'm just going to tell you guys right now is this. If it's on the AP test, you are going to be allowed to use your calculator, so if you want to, you can look back at your trig pre-calc notes to brush up on exactly how to do this by hand, but we're going to concentrate really on how to do this in a calculator. So first thing you got to do is turn your calculator on, and I really hope you guys can see that. Is that good enough for you guys to see? All right, I'm going to lead you guys through how to graph this first one right here, where x equals cosine of t, y equals sine of t, for t in the interval from 0 to 2 pi. And in order to use a calculator for this, first you need to ask it really politely to graph in parametric mode. So you can go into into the mode screen, scroll down to, it looks like about the fourth or fifth line there. It'll start out with function or fn, depending on what kind of screen you have. And you just want to switch it over to parametric. And in case I haven't emphasized this enough this year, make sure you are in radian mode. When you hit the y equals menu, you're going to see you now have actually x1t, y1t, x2t, y2t, etc., etc., etc. In order to graph this function, all you really have to do is type in where it says x equals cosine of t and y equals sine of t. Just literally type in x equals cosine of t. Nice little life hack here is this isn't actually the x button. This is the independent variable button, so you can push that and you get cosine of t. That way you don't have to hit alpha t for it. Sine of t, and now we're going to go over to the window to try to adjust it to be exactly what we want. And you can see up here, your book, AP, anything is really going to give you the interval over which to graph this. So the interval that's going to be good is going to be from 0 to 2 pi. And you can see that converts right to 6.28, blah, 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 blah. Hey, by the way, happy Pi Day, Saturday. I happen to know how this function works out, or this parametric curve works out, so I'm actually going to change my x-min to -2, x-max to +2, same thing with y-min and y-max, and then I simply hit graph, and it graphs the function, and what you can see, we actually have a circle, is what is graphed here. So in order to get that on my paper, let's just label this as number 1 right here. I'm just going to copy that right onto my paper. Doesn't have to be overly great. I mean, it looks like the circle has a radius of 1, and we just have to sketch it in there. And my artistic ability definitely shows on that one. Now, what you do have to be aware of here is we actually have 3 variables going on, so we do have to graph the 3 dimensions. If you remember back to when we graphed this, it actually showed that it graphed in a counterclockwise fashion. if you fail to recognize that, you can actually hit trace, and you should be able to see right there a particle shows up. And if you hit right, that advances the particle in the forward trajectory. If you hit left, it's in the backward trajectory. And just looking at that, I can see that this circle, the particle is traversing it in a counterclockwise fashion. And so I just have to draw the motion in there. All right, so there is our graph. And actually, this shouldn't be a surprise, considering x is cosine of t, y is sine of t. This is really just the unit circle that we're graphing here over one period of the unit circle there. So right now, I'm going to pause for about 5 seconds. You can pause the screen. Again, you're on YouTube. Pause it. Try to do these two. Then hit play. You can either look at the next page to see the answers, or I'm going to put them up here in just a second. So I'm going to count to 5. Oops. And a little bit more just so you can see number 3. And let's flip this so that you can actually see. There's the answers. It looks like the first one was a circle going in the counterclockwise fashion. Number 2 will be an ellipse where our major axis runs vertically, and it looks like the major axis is 10, minor axis is horizontal, and the minor axis is, it looks like 6 across there. And then it looks like on number 3, we've actually graphed what appears to be half of a parabola. All right, cool. Now let's go forward and figure out how to do calculus. Ah! So you can see right here, we have formulas on how to find slope and the second derivative to help determine concavity. Again, I'm going to read through these. If you need more time, come back, pause, and then write it in your notes. But again, I don't want to take too much time. So you can see to find dy dx, what we've traditionally labeled as the first derivative, you're going to find dy dt and divide it by dx dt. And that'll allow you to give slope at any point, or at any time t. Down here, we have finding the second derivative. To find the second derivative, you find, well, the derivative of y prime and divide it by dx dt. So we take the answer from the first part, that's right here, and then divide it by the same dx dt down here. And this, just to remind you guys, can help us determine concavity. So right now I'm going to pause for about 5 seconds. If you want to pause the screen and get these down, you can. And shouldn't be a huge surprise, we are actually going to do these problems now. So you can see I've got finding dy dx. The first set of parametrized curves that we're going to do is x equals t squared minus 3t and y equals t cubed. In order to find dy dx, let's just call that a, we have to find dx dt and dy dt. The dx dt, you can just see right here, x is t squared minus 3t. I'll pause for a second while you contemplate to yourself how to find the derivative of that using our derivative rules. And of course, we've got 2t minus 3 for dx dt. Dy dt, we've actually got, pause there for a second. It is 3t squared. To find dy dx, huge surprise, we have to do dy dt divided by dx dt. That's going to give us 3t squared divided by 2t minus 3. Cool? That's part A. You're done with part A. For part B, a little bit trickier. You have to find the derivative of this and divide it by, this, the 2t minus 3. Now pause for a second while you guys contemplate how bad this is. Again, there's the answer to A. We're going to have to do quotient rule here. That kind of stinks. To find that dy prime over dt, that's again going to be the low d high minus high a d low over a low. Alright, cool. So there's using the quotient rule. We really just want to clean this up a little bit. We're going to have, let's see, 12t squared minus 18t minus, looks like a little, 6t squared all over 2t minus 3 squared. Let me scooch that up a little bit so you guys can actually see that. So now, that's not what B is actually asking for. B here is actually asking for d2y over dx2. That's the second derivative of y with respect to x. To make this with respect to x, to get that d2y over dx2, we have to take this expression, again, 12t squared minus 6t, I think that's going to be 6t squared minus 18t over 2t minus 3 squared, and divide it by the dx dt. If only I had written that down. Oh, hey, it's right up here. Divided by 2t minus 3. That is an answer. If this is a free response question, that is acceptable to leave it just like that. Now, we know that we're better than that. We're not actually going to leave it just like that. I would actually put it as 6t squared minus 18t all over 2t minus 3 cubed as my final answer, just to make it a little bit, not so ugly on that one. Let's see. Can I actually get that one? Yeah, I think I did. 3t squared minus over 2t minus 3 for the first derivative. Second derivative, 6t squared minus 18t over 2t minus 3 cubed. So there's the first one. Right? Not too awful. Let's look at that second one. I mean, you might want to pause the video for a second and see if you can do this one. I mean, really, if I'm giving you guys a heads up on this one, what's going to make this easier is to use some of our logarithmic rules. So, logarithm of a product is the same thing as a sum of two logarithms. Looking over here, an exponent, we can actually bring that 4 down. We've got 4 ln of 3t, which is going to be the same thing as 4 times the quantity of ln of 3 plus ln of t, which, just because I know where this is going, I'm going to redistribute that 4. I've got 4 ln of 3 plus 4 ln of t. And all of this is just to get to, all I'm trying to say is use your logarithmic properties. It makes it a little bit easier, because now when I do a, and I find dx dt on that one, dx dt, that can't be this simple. ln of 2, that's just a constant, so that's going to be 0. Plus the derivative of ln of t, that's just 1 over t. dy dt, this is going to be pretty simple as well, because 4 ln of 3, I really don't care what that number is. All I know is it's a constant. 4 times ln of t, the derivative there, you're going to have 4 times 1 over t, or just 4 over t. When we look at what our dy dx is, then we've got 4 over t divided by 1 over t, which this can't be. No. 4 over t times t over 1. Those t's cross out. I'm just left with 4. Well, that's pretty cool. That means that the slope of this set of parametric curves is 4. Now let me do some quick calculations here. If I'm thinking about what type of figure has a constant slope, can you guys say it with me? This is a graph of a line. So you can actually plug this into your calculator and you can actually see that this ends up being the graph of a line, which if I look at part B to find d2y dx2, really what I do on this one is I find the derivative of dy dx, the derivative of 4 dy prime over dt is going to be equal to, well, just 0. Looking at my second derivative, d2y over dx2, that's going to be 0 over, I don't care what it's over, because 0 divided by anything other than 0 is going to be 0. And I look up here, dx dt was 1 over t, so this ends up being 0. What this actually indicates to me is this function has no concavity. Again, it's a line. And if you don't believe me, just grab your good old fancy graphing machine and get that graph. All right? Oh, hey, look at that. Look at that work. Isn't that pretty? I think I did it a little bit harder, a more difficult way. Whew, man, this is a lot. Okay, let me read this. Consider the curve defined parametrically by x equals t squared plus 2 and y equals cosine of t for 0 less than equal t less than equal 2 pi. Man, that's a lot to read there. A, sketch the curve in the viewing window, -5 to 45 by -2 to 2. Okay, so that means these are the x's, these are the y's, and hey, over here I have my t's. I mean, really, it tells me exactly what my graph is supposed to be here. T squared plus 2. Let's see, down here I've got cosine of t. Changing my window a little bit, it looks like I want 0 to 2 pi. Okay, that's good. -5 to 45. Probably don't want to count by 1s. Maybe count by 5s there. -2 to 2. That was already done for me. Alright, and now we hit trace. Okay, cool. We saw it goes from left to right as we graph it. So for part A, all I need to do is copy what is on my screen. And if I didn't have these helpful hints up here, I would have to play around with it to get the actual good window on that. And indicate direction. Okay, there's the trick precalc stuff out of the way. Lowest point on the curve. Okay, looks like the lowest point is right about here. Done, right? Haha, no. I can't do that. I actually have to use some calculus for this. So what I'm actually trying to do here is I'm trying to find out it's going down and then it comes back up. Really what I'm trying to do here is down and up. Those are just vertical directions. And vertical directions, that's indicating y. So if I want to find the lowest point, lowest implies the minimum of y. And it seems to me, I taught you guys how to find a minimum. To find a minimum, what you have to do is find dy dt, which, if I'm not mistaken here, the derivative of cosine, negative sine of t. And to find the minimum, I just want to set that equal to 0. Sine of t is going to be equal to 0 at t equals 0, t equals pi, and t equals 2 pi. And if you don't know how I got those, unit circle. So now looking at this, in order to find out which one is actually my minimum, well, I mean, just looking at it, it looks like in the middle, so I'm guessing it's going to be pi. But looking at this, I actually have to do my analysis on this one. So I've got dy dt. Analyzing this, I know I have to put 0, pi, and 2 pi all on my number line. And in order to find out whether this is a minimum or a maximum, I have to find out between 0 and pi, dy dt, is it negative or positive? Well, I mean, just plugging in pi over 4, I've got sine of pi over 4 is root 2 over 2, negative root 2 over 2, because I got that negative. It doesn't matter what the value is, I just care that it's negative. Between pi and 2 pi, I could plug in like 3 pi over 2. Sine of 3 pi over 2 is negative 1, negative, negative 1. I know I've got a positive here. So looking at that, I can actually see that I've got a minimum at, what did I say? T equals pi. So here we actually do want to find the lowest point on the curve. So what we actually have to do, I have to find out that x is equal to it's t squared plus 2. So that would be pi squared plus 2. I don't know what that is. I can plug that into a calculator in just a minute. Let's just get y hammered out here. Y is going to be cosine of pi. So cosine of pi gives me negative 1. So let's just go back over here. In order to find out what that point is, I'm actually just going to really use my calculator on this one. I'm on trace. If I type in pi, down here, if you can't read it, it actually says t equals pi. I hit enter, and the particle's now actually at the lowest point. And I don't know if you guys can read that, but I've got my x is approximately 11.870. It was 11.869604. So it gives me 11.870. And the y coordinate is actually listed there as negative 1 as well. So my lowest point is approximately 11.870, comma, negative 1. Boom. There. Done. Okay. Part C, all points of inflection. That kind of stinks. All points of inflection means for points of inflection, I've got to find my second derivative. So to find my second derivative, let's see, I've got to find my first derivative first. So dx dt is equal to 2t. Okay, 2t. dy dt, I've already got it written out, but I'll just write it down again. Negative sine of t, which means dy dx is equal to negative sine of t over 2t. Bueno. Now to find the second derivative, I find dy prime dt, which is equal to, okay, so low 2t d high negative cosine of t, oh man, this stinks, minus high d low all over low squared, where was it? Oh, 2t squared. Okay, let's see if we can simplify this a little bit. So negative 2t cosine of t plus 2 sine of t over 4t squared, aka negative t cosine of t plus sine of t all over 2t squared. And now, in order to find out, oh, no, actually, now I need to actually find out d2y over dx2. You got to keep paying attention if I'm going off the screen here. I apologize if I do. I actually have to take this and divide it by 2t. So I'm going to have that negative t cosine of t plus sine of t all over 2t squared times 2t, so 4t cubed. I want to find out where this is 0 or undefined. Well, it's very easily undefined at t equals 0. In order to find out where it's 0 and to find the point of inflection, here's a nice little strategy for you guys. I'm going to take my calculator. I'm going to put it back into function mode. I'm just going to plug this into my calculator. Alpha y equals fraction, negative t, it's an x in case you can't read that, cosine of t plus sine of t all over 4t cubed. And then I just look at my graph. Oh, no, let's make this viewing window because I'm only concerned t between 0 and 2 pi. I'm going to go from 0 to 2 pi on my x-min and x-max. And now I can actually see graphing, 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 graphing. Hey, it just passed over the x-axis. So it's right about here that I have my point of inflection. In order to find out where that point of inflection actually is, second calc, 0. Let's see, y is 0.024, so that's above the x-axis. I just go over until it's below the x-axis, slowly, slowly, slowly. It's now negative 0.002, so now I just hit enter again, and my 0 occurs at t is approximately 4.493. Boom. Done. Here. I'm not going to bore you too much with this one. It's pretty much the same type of problem, but now here I'm talking about rightmost point. So the only thing to keep in mind here, everything else is exactly the same, but rightmost means you are maximizing the horizontal nature. So if it ever says anything about rightmost or leftmost, that means you want to minimize or maximize the horizontal component of the motion. That would be the x coordinate. So in this case, to find the rightmost point, you just take the derivative, set it equal to 0, and analyze to find the maximum there. And we'll pause. Well, you can look at that beautiful handiwork right there. Isn't that amazing? Yeah, I thought so. Woohoo! All right, cool. So we're just gonna do. I'm gonna go out on a limb and just say let's just do one of these, and then you can actually see the work for the other one. So I'm just gonna choose this one, just for fun. All right. So I want to find out where I have the tangent line being horizontal and where I have the tangent line being vertical. What I have to keep in mind here is my slope at any given point is given by dy dx. And dy dx in this case is given by dy dt over dx dt. So what I can see here, for a slope, for a tangent line to be horizontal, my slope would be 0. The only way to get a fraction to be 0 is to have your numerator be 0. So for a horizontal tangent line, that is where your dy dt is equal to 0. Conversely, if I want to find out where the tangent line is vertical, that means your slope is undefined. And to get an undefined slope, your denominator has to be 0. So for vertical, that's where dx dt is equal to 0. So this is the way that I remember it, is by relating it back to slope. You could just memorize horizontal dy dt is equal to 0, vertical dx dt is equal to 0. Either way, you're going to get the same. You're going to get to the same location. Here for part A, I want to find out where it's horizontal tangent line. So horizontal tangent line is going to be at dy dt equals 0. So dy dt is equal to 3 cosine of t set that equal to 0 at t equals, and I'm just going to go through one iteration of one period of the unit circle. So looking at that, cosine is equal to 0 at pi over 2, 3 pi over 2. And really, I would want to find points at which where the horizontal tangent lines occur. So for at pi over 2, t equals pi over 2, what I'm going to do is find my x is equal to -2 plus cosine of pi over 2. My y is going to be equal to 1 plus 3 sine of pi over 2. And just doing some rough math here, we already figured out cosine of pi over 2 is 0. Duh. -2 plus 0 gives me -2. 1 plus sine of pi over 2 is 1. 1 plus 3 gives me 4. So the point for my horizontal tangent is at -2, 4. And we're going to grab my calculator here in just a second and just make sure that that works out. At t equals 3 pi over 2, I do the exact same thing, except obviously instead of doing cosine of pi over 2, this time I'm going to do 3 pi over 2, and y is equal to 1 plus 3 sine of pi over 2, and cosine of pi over 2 is the same thing. 3 pi over 2 is the same thing as cosine of pi over 2, so this would be -2. So sine of, that was 3 pi over 2. I can't believe I missed that 3. Sine of 3 pi over 2 is -1, so 1 plus 3 times -1 gives me, -2, right? Yeah, okay, cool. So this horizontal tangent occurs at -2, -2. So just to be clear, my two horizontal tangents, horizontal lines, have an equation of y equals. So I've got y equals 4 and y equals -2. Now all that's left is to do b. b is the same thing, except this time I'm trying to find vertical, so dx dt equals 0. So dx dt, just looking at that, that is the negative sine of t equals 0 at t equals 0. And pi, I'm going to neglect 2 pi because that would just loop it right back around. And now looking here, I've got t equals 0, means x is equal to -2 plus cosine of 0. Y is equal to 1 plus 3 sine of 0. Cosine of 0, 1, -2 plus 1 gives me -1. Sine of 0, 0. 1 plus 0 gives me 1. So one of my locations for a vertical tangent is going to be -1, 1. Other one, t equals pi. I've got x equals -2 plus cosine of pi. Y is equal to 1 plus 3 sine of pi. Cosine of pi, -1, -2 plus -1 gives me -3. Sine of pi is 0. That gives me 1. So I've got -3, 1. And I can see my vertical tangents. Vertical lines have an equation of x equals, so it's at x equals -1 and x equals -3. Now grabbing my calculator over here just to make sure that all of these answers make perfect sense. Go back into Parametric, clear these out. -2 plus cosine of t. Oopsies, wasn't on x1. -2 plus cosine of t, clear that out. 1 plus 3 sine of t. And let's just hit zoom 6, and you can actually see If I've got t equals 0, t equals 0 was at negative 1, 1. There's my vertical tangent. T equals pi over 2. There's my horizontal tangent. T equals pi. Vertical tangent. And t equals 3 pi over 2. There's where my horizontal tangent is. Cool. Cool beans. Cool beans. Do people still say cool beans? I'm not entirely sure on that. You guys know I'm not that cool. Hey, good news. We've only got one thing left. And hopefully I can get it before my battery dies. Fingers crossed. If not, I'll just add another video. This is how to find the length of a parametric curve. T increases from t1 to t2. Take dx dt, take dy dt, and plug it into this equation. The length is equal to integral from t1 to t2 of the square root of dx dt squared plus dy dt squared dt, and then blah, blah, blah. Somebody has pointed out, and I've pointed it out to myself repeatedly, that this looks extremely like the length of a curve using a function. If you want to see that, pause it, take a picture, because we've got some work to do. So looking at this, finding the length of the curve, just real quick, I've got x equals sine t, y equals cosine of t. If only I knew what that looked like. I find dx dt, which is equal to, whoopsies, no, take the derivative, cosine of t. I find dy dt, it is equal to negative sine of t. I plug it into the formula. Arc length is equal to integral from t1 to t2, 0 to 2 pi of the square root of cosine of t squared plus negative sine of t squared dt. Plug that into your calculator if you want to. Of course, I'm just seeing some stuff here. 0 to 2 pi, square root. I know that I write this as cosine squared of t plus sine squared of t dt. If only I knew what cosine squared plus sine squared was. For those of you following along at home, hopefully remember cosine squared plus sine squared equal to 1. Square root of 1 is just 1. Now I've got the integral of a constant function. I know that that is just integrand times the length of the interval, which is just 2 pi. Of course, you could plug this into your calculator if you wanted to and just get 6.28, whatever it is. I don't know. I don't memorize mathematical constants. I'll leave that for other people. And you can see the work over here. And I think my battery is about to die. I'm just going to put this up here, the length of the asteroid. It ends up being 6. So that was it. This is posted on my website as well. So that was fun, guys. Let's do this again sometime.